Hi, this is Professor Fernandez, and this is video 2 in lesson 27. So we're talking here about u-substitution in the integration for transcendental functions as your integrand. And there's a lot to say here, so you can see that even though I only have 3 examples on the screen, there's about 8 subparts that we are going to work through throughout this video. And these examples come from Calculus Simplified. So because we are going to be talking about u-substitution, the first thing I want to make sure is that you're comfortable with u-substitution as a technique before we start in this video using it, applying it to transcendental function integrands. So check out videos 19.1a through 19.1c for a review of u-substitution. Anyway, I'll, of course, talk briefly about the main takeaways and kind of rules of thumb as we go through the video. So let's take a look at the first one here. I should also mention you might want to take a look at video 27.1, the one right before this one, which talks about integration rules for exponentials, for 1 over x, for example, and for sine and cosine. And so that is something else we're going to use throughout this video. Okay, so let's take a look at these 3 here. The first example here, 2x e to the x squared. As always, integration is difficult because we don't really know what technique to use before, once we start integrating. With u-substitution, certainly this video is all about that, so we're going to have to use u-substitution across all these examples. But how would you know to use u-substitution for this integral if you didn't already know or were told that you're going to have to use it? So the answer is, you try the usual things. I'll zoom in a little bit more here. If this were integral of 2x, then I could probably do that. Or integral of e to the x, I could do that, without using integration by u-substitution. However, it's not. So u-substitution is a really useful technique when there is some function in the integrand whose derivative is also in the integrand. Alternatively, one of the other rules of thumb I gave in earlier videos is if you can spot a composite function in the integrand, then, composite function, something like f of g of x, then that's a good tip-off that this is probably a u-substitution problem, and you can try the inner function as your u. So we do see a composite function here. We see a product, certainly, of 2x and then e to the x squared. There's also a composite function, which is this one right here. Rather than being e to the x, it's e to the x squared, or x squared has been put in for where x used to be. So that is a tip-off, right? This composite function, and I'm going to look at the inner function here, which is x squared. So I'm going to try u equals x squared. And then let's go through with the substitution process here. The differential is the derivative, 2x times dx. And then notice that, again, because of the way I've designed it for this video, this is exactly everything that is given in the integral. So we're going to start substituting things in. So e to the x squared here becomes e to the u, and then 2x dx is exactly what du is. And remember, I talked in the videos that I mentioned that you might want to review about 2 different ways when it comes to definite integrals that you can deploy u-substitution. One of them is what I'm going to do here, which is I'm just going to focus on finding the antiderivative. In other words, I'm going to ignore the limits of integration. And then once I find the antiderivative in terms of the original variable, x in this case, I will return to the problem of making sure I factor in these limits of integration using the evaluation theorem. So I'm just integrating e to the u, and at this point I know what that integral is. That was the video 27.1 we reviewed. That's e to the u. I'll put the plus c because I am doing an indefinite integral here, but if I then go back and rewrite this in terms of x, right, this is e to the x squared plus c. So in other words, I have just found out that the antiderivative of 2x e to the x squared dx is e to the x squared, plus some arbitrary constant. So what I can do with this is I can say, oh, great. So now I'm going to go back to my original problem, which is this one, and I'm going to say that the integral from 0 to 1 of 2x e to the x squared, now it's a definite integral, is going to be e to the x squared evaluated from 0 to 1. So I'm using here the evaluation theorem. So I'm going to substitute in 1 for x, subtract, substitute in 0 for x, and that will be my answer. So I have e minus e to the 0 is 1, so I just have e minus 1. That's my answer. Great. So A is done. Let's see if we can speed things up a little bit here for the rest of them. So let's look at b. Zoom in here. This is 1 over x plus 1. If this were 1 over x, then I would know that the integral is natural log of the absolute value of x. We covered that in the previous video. But it's not. It's 1 over x plus 1. That's okay because, this is a composite function in disguise. It's 1 over x, where for the x we have substituted in x plus 1. So that's how we view this as a composite function. So let's let this be u. U is x plus 1. The differential is the derivative, which is 1 times dx. And then we're going to just put everything into the integral. It's indefinite, so that's great. We're not going to have to do any of the stuff we just did with the evaluation theorem. So 1 over x plus 1 becomes 1 over u. And then du is just dx, right? It's 1 dx. So I've replaced dx with du. And voila, the antiderivative of 1 over u is ln of absolute value of u plus c. Then I go back, replace my u with the expression in terms of x. That's it. Ln of absolute value of x plus 1 plus c is the answer. Great. So let's look at part c. This one is more involved. Again, how would I know what to do with this? One thing you can always do, and I always suggest, is to simplify, especially when you have a complicated expression like this. How could I simplify? Well, the first thing you might notice is that if I rearrange things around, right, here's an x squared plus 1, here's an x squared plus 1. So let me write this as x squared plus 1 plus 2x, all divided by x squared plus 1. You might be thinking, I wouldn't have thought to do that. And I would say that's okay. That's the purpose of watching these videos, right? To be introduced to other ways of thinking and strategies for solving these problems. And now I can divide this out. So x squared plus 1 divided by x squared plus 1 plus 2x over x squared plus 1. And then this part gives me 1, right? I don't have to worry that x squared plus 1 is ever 0. It never is in this class, so I can divide that out safely. And I'm left with 2x over x squared plus 1. You can see why this is part C in the examples that I'm doing, because it's requiring more work. And it will require even more work in a minute. So the original statement of the problem, there we go. We have now converted into 2 different integrals, and they are going to require different integration techniques. The first one, integral of 1 dx, that is just x. So that's not something that requires u-substitution, but the second one over here does. And how would I know to do u-substitution here? Well, again, if there's a function that is a composite function, that's a tip-off, or as I said earlier, if there's a function whose derivative is in the integrand, that's also another way that you can try u-substitution. And that's the case here. So x squared plus 1, right? Its derivative is 2x. It's upstairs. So that is a good sign that we can let u be x squared plus 1. And its derivative will be the derivative of this, which is 2x times dx. And then I go off and I employ all these substitutions to see what my integral turns into. So I'll do it, let's see, over here. So this integral, x squared plus 1 is in the denominator. That is the u, so that's a u down there. And then 2x dx is exactly du. So it's 1 du. And this is the integral we just finished talking about and doing. So that's ln of the absolute value of u plus c. And then written back in terms of what u is in this problem, right? X squared plus 1 plus c. Okay, so I'm going to translate that back over here. So ln of x squared plus 1 plus c. Okay, so I'll zoom in so you can see the full answer there. You might be wondering, why did I drop the absolute values, right? How come they turn into parentheses? Remember, absolute values' sole function is to make the interior of whatever, the absolute value you're taking, non-negative. But x squared plus 1 is never negative. It's never even 0, right? It's always at least 1. So we can safely drop the absolute values and just put parentheses. Minor technical note, but again, it helps to be able to see how things change and why things change if you look at an answer, for example, in a book or something. All right, so that is it for these 3 first preliminary type of examples, and you can see again the progression in difficulty from A to C. All right, let's switch gears a little bit now And let's talk about integrating these two functions here. We got tangent and cotangent. You might think, first of all, that this is not a u-substitution problem. I don't see any of the things that you, Professor Fernandez, just mentioned at the start of the video. I don't see a function, a composite function, and I don't see a function whose derivative is also in the integrand. But I would say, wait, the other thing I said in the video, which is simplify first. So let's take tangent. We know that tangent is sine over cosine, and that is the first tip-off. That, in fact, this is going to be a u-substitution integral. So how would I know that? Well, back to that notion, right? Is there a function whose derivative is also in the integrand? Yes. So the function cosine, its derivative is sort of in the integrand, right? The derivative of cosine is negative sine. We'll have to, we need a negative sign, basically, but we'll take care of that in a moment. Let me just mention, what's another thing you could have said? You could have said, hey, the derivative of sine is cosine. So why don't I take this to be my u, and then du is cosine of x dx. But then look at what we would have. So we would have the integral of u, and then some strangeness of du over dx here, and then this would turn into u over du times dx squared. This is the math telling you that this is not the way to go, right? We don't want to do this. So let's try something else. So while there are two feasible choices for u from this form of tangent, really there's only one that's going to work out in terms of what integration results we have, which is the one where u is cosine. So if u is cosine x, then the derivative is minus sine x dx. We don't have the minus, so we divide by minus or multiply by minus 1, whichever way you want to think about it, and we get what is in the integrand. So this part, sine x over dx, that is going to be replaced with du. So if I go down here, I say, okay, this is going to be minus du, right? That's all of this, divided by this cosine x was just u. And here we are once again calculating the antiderivative of 1 over u du, which is natural log of the absolute value of u. And u was cosine of x, so absolute value of cosine of x plus c. And then this is where you could leave it this way, or you could use the fact that, remember, with logarithms, right, this minus sign can be put up here as a power, cosine of x to the negative 1. And then I can write this as a reciprocal, 1 over cosine of x. And then I can remember that 1 over cosine of x this is one of the reciprocal trig functions, which is secant x plus c. So long story short, the integral of tangent is natural log of secant x plus c. This is actually a integral you might see in an integral table, kind of like the integral of sine or integral of cosine or something. But this is the calculation that we just done to run through. This is the way that you show that, in fact, the integral of tangent is natural log of secant. Okay, so let me make some more room for myself and erase what is over here so we can do part B. So let's take a look at that one. That one is integral of cotangent. So I've just taken the reciprocal of tangent, and let's see what happens there. So integral of cotangent, that is cosine x over sine x. For all the same reasons, right, we do have those two feasible choices for u. U could be this or u could be that, but for the same reason that just happened, right, we want to choose u to be the thing in the denominator so that the du ends up upstairs in the numerator where it's supposed to be for us to be able to integrate it using the formulas and techniques we know. So let's let u be sine x, and let's du then becomes the derivative cosine x dx. And the integral converts to, in the denominator, we have u. And then this one, we don't need to do anything with the negative signs, right? Cosine x dx, right? That is all du. So we're back to the same thing, integrating 1 over u, ln absolute value of u, substitute back in what u is, which is sine x plus c, and there we go. So the integral of cotangent is natural log of absolute value of sine. And that's it for that one. Okay, I have 3 more for you. So the purpose of these 3 is to bring together some of what we've just been talking about. Remember that in the very first example, we had a product of two functions, but really we thought of it as one of them is a composite function, e to the x squared, and the inner function, its derivative is over here. So this is a very natural u-substitution problem. Notice that a very similar thing is happening here. I have a product of two functions. However, the inner function of this cosine of x cubed composite function, the inner function u, which is x cubed, its derivative, quote unquote, is out here in the integrand as a multiplicative function. Not really, right? The derivative of x cubed is 3x squared, but the factors can always be, divided, multiplied, and gotten out of the way. So this is another tip-off that this integral is a u-substitution integral. So we're going to let u be x cubed. Du is derivative times dx. We don't have a 3 in the integrand, so we're going to get rid of the 3 by dividing by it, right? Leaving us with x squared dx. And that is exactly all we need. So x squared dx, here is x squared dx. So this integral, all of that turns into 1/3 du. And then cosine of x cubed is u, so I'm integrating cosine of u, du. And I know that the antiderivative of cosine is sine. And then I go back and I substitute in what my u was, which was x cubed. And there we go. I am done with that one. I should have mentioned, but I think at this point in the course and in the videos being lesson 27, it's understood that you can check your work, right? So you don't have to rely on faith that this is in fact the antiderivative. You could differentiate this function and verify that the derivative is x squared cosine of x cubed. Certainly, you might make a mistake in calculating that derivative, so you can try to verify your verification by using, Wolfram Alpha or some other online resource to double check your differentiation. Okay, how about integral of secant squared 2x? So the 2x there is a tip-off. Again, this is a composite function, so the inner function is 2x. So let's try that as our u. So u is 2x, and what is the derivative? Well, the derivative is 2 dx. We don't have a 2 anywhere, so again, we divide by 2 to give us what we do have, which is just dx. And then we start substituting things in. So this will be 1/2 antiderivative of du times secant squared of u. And secant squared u, this is one of those integrals that we should know from all the tables of integration of what's the integral of sine, cosine, tangent, things like that. We know, for example, the derivative of tangent is secant squared. So the antiderivative of secant squared is tangent plus c here. And then we substitute in our u, which was 2x, so tangent of 2x plus c. And that's our final answer. Great. And then we got one more to do. This one is a definite integral. For all the reasons that I mentioned before, I'm going to go ahead and find the antiderivative first and then worry about the limits of integration. So change the problem a little bit. Let's first find antiderivative of 2x, of cosine 2x dx. Okay, another composite function. Notice the 2x here. So let's try that as the u. And then the derivative is 2 dx, the differential. So I don't have a 2, I divide by it. 1/2 du is dx. So I start then substituting everything. 1/2 du, that's the dx, and then the cosine of 2x becomes cosine of u. Integral of cosine is sine. Put back in the u, sine 2x plus c, and then now I have my antiderivative. So going back to the original problem, which was integral from 0 to pi over 4 of cosine of 2x. Now I know that I have this antiderivative, and I'm going to evaluate that from 0 to pi over 4. So I just have to calculate the f of b minus f of a step here. All right, so I get sine of 2 times pi over 4 minus sine of 2 times 0. So that's me putting in pi over 4 for x over here, and then subtracting, putting in 0 for x over there. Okay, so simplify a little bit more, right? The 2 cancels with that one, so I get sine of pi over 2 minus this is sine of 0. Okay, Sine of 0 is 0, so that doesn't change anything. And then sine of pi over 2, that's one of our fundamental values, which is 1. So I get half times 1, so just 1/2. That's my answer for that one. All right, so scrolling out and zooming out, a couple of things to mention here. Be very careful when you are applying the u-substitution to take care to make sure that you're getting the right u. How do you know which u to choose? Well, I've given you some good insights and in earlier videos also. If you see a composite function, try the inner function as the u. But over here, you might think, I don't really see the composite function, even though we could think of this as like 1 over u, where u is x plus 1, and in fact, that's exactly how we solved it. And certainly over here, I just don't see a composite function. So a combination of algebra, if you see a composite function, try the inner function as a u, but also trying to look at, find a function whose derivative is also in the integrand. Right? That's also what we did here. The derivative of x cubed is 3x squared. It's here without the 3, but if you wanted the 3 there, you would just divide by 3 to not change the original expression. And then last thing to mention, as this discussion made clear, sometimes you do all of that and you find multiple choices for u that seem to work. But then when you carry through the substitution, you get some weirdness. You might get integral of some number divided by du. Right, so all our du's should be not in denominators, right? They belong out here for all the reasons that we talked about in Chapter 5 in Calculus Simplified and what this differential really means and where it comes from. Traces back to the width of these rectangles that are involved in just the concept of integration. Okay, so all that being said, thanks for watching.